Hello and welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of science that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Hugh Ross. I'm the founder of Reasons to Believe, and today I'm going to be joined by another astronomer, Brian Keating, from the University of California, San Diego, and we'll be your guide as we explore what's going on in the early history of the universe and some of these amazing new telescopes that are giving us insights like we've never had before on the beginning of the universe. But before we get into this discussion, I wanted to encourage you to subscribe to our YouTube channel, Reasons to Believe YouTube, and click on the bell icon so that you can be informed of our new videos. And learn more at reasons.org or by following us on social media at RTB_official. Well, Brian, I've been reading your book, Losing the Nobel Prize, and it brings back a lot of memories of what happened when the BICEP2 team basically jumped the gun. So, and the insights you give on just how much the Nobel Prize motivates people in a good way and some ways not so good. So I really enjoyed the book, especially enjoyed all the stories you told about people I knew personally, people like Bob Dickey and I knew both of the Burbages.
Oh, wow.
So, in fact, when I arrived at Caltech, the first phone call I got was from Jeffrey, and he said, "We want you to come down." So I was only at Caltech a week. I drove down to give a colloquium there, and it was really good just meeting the astronomy faculty there.
It was a giant,
we have a lot of connections there, even though we're a generation apart from one another. So I think we got a lot of fun things we can talk about. But we're not going to go there. What I really want to talk about is the research you've done on the cosmic microwave background radiation. And what amazes me about reading your papers is you've been involved in almost all the ground-based cosmic background radiation telescopes that are out there. I mean, we got BICEP, BICEP2, the polar bear, and now you got this new thing that you're in charge of that I want to hear about. Apparently you got first light just a little while ago. So, and where we want to go with this is that, this is actually a recording that we're going to make available to our scholars that are participating in our workshop on what the James Webb Space Telescope has been discovering. But in some cases, and I think you would agree with this, is that we also need to give attention to other instruments that are exploring parts of the early history of the universe that James Webb can't explore. And really, astronomers' goal is to integrate across the entire time scale of the history of the universe. So, and what's interesting is these different instruments that you've been part of actually give us insights on what's going on in the early history of the universe. So, as a beginning, why don't you just start off with what was your first involvement with experiments on maybe we better back up one more. What is the cosmic background radiation, the radiation left over from the cosmic creation event, and maybe what motivated you to begin to pursue that research?
Well, the cosmic microwave background is sort of the ultimate wallpaper of the cosmos. It's the oldest possible light that you could actually observe. And it's not in the form of visible light like you and I are seeing right now. It's in the form of microwaves, which are useful for many things, heating up coffee cups to observing the early universe. And that's by virtue of the fact that the universe has been expanding since its birth, since its origin. And that expansion has taken the primordial heat, the fire that was the leftover heat from the fusion of the first nuclei on the periodic table. There are nuclei like hydrogen, helium, and lithium, and they're isotopes. And they are only forged in extremely high temperature, high density reactions like the center of stars or reactors on Earth, perhaps. But that's really it, except for the first few minutes of the universe's history. And I always joke that, the time it took to make the first elements on the periodic table is about half the time that it takes to watch an episode of The Big Bang Theory. So that process of fusion always results in leftover heat, which is why we think we can use fusion on Earth to make nuclear power reactors, to have electricity that's too cheap to meter, as they say. that leftover heat then existed in a plasma, which is completely opaque and is not possible to see through a plasma any more than you can see through a mirror, which is a type of a plasma if you think about it. And that lasted until the universe cooled sufficiently such that the first protons and electrons could fuse together. We don't normally call it that, but that's what they did. They combined together to make the first atoms. So first came the nuclei. First there was energy in the beginning. There was really truly light, and that light was pure energy, and that energy eventually created matter, and the matter then created nuclei. The nuclei then didn't interact with anything other than the heat that was there for 380,000 years. And then the universe cooled sufficiently that sort of the condensation or fusion of the first atoms of hydrogen formed. And at that point, the universe became transparent, and light that had existed then could then freely stream and propagate to telescopes to our very location here on Earth. In 1964 and 63 and 62, my PhD advisor, David Wilkinson at Princeton, who you shortly know, was the late David Wilkinson. He and his advisor and colleague, Bob Dickey, who's a titan of physics in the early and later parts of the 20th century, they realized what these two astronomers, but they really weren't working on astronomy. They were working on the first telecommunications satellite at nearby Bell Laboratories, Holmdel, New Jersey. And as a New Yorker, it pains me to admit that the origin of the universe in this sense was discovered in Holmdel, New Jersey, of all places. But when they discovered it, they were looking at the first telecommunications satellites. And no matter what they did, this is in the aftermath of Sputnik and everything else, and the U.S. was far behind in the space race, they found that they were far behind and they were losing the communications race, because every time they look at this satellite called the Echo satellite, they were getting this excess noise and hiss and hum that was coming at all times of the year, all times of the day, no matter where they looked, when they looked, how they looked, they couldn't get rid of this. Penzias and Wilson were their names. And they called up Bob Dickey and Wilkinson and others and Jim Peebles, and they said, well, this is what we're finding. We heard from a radio astronomer friend that you might have some ideas about it to help us out. Their paper, Penzias and Wilson's paper, was very dry. It was called an excess of antenna temperature at 4,030 megacycles per second. You would never think that would be a Nobel Prize worthy of really.
It's only basically a page long,
yeah,
too.
It's
very
long.
short.
And in it, what's so interesting, in it and the companion paper that Dickey, Peebles, Roll, and Wilkinson wrote, nowhere, not once, is the words Big Bang mentioned.
Right.
They actually assume that the universe came from a pre-existing collapse of another universe or a cyclical universe, which interestingly is becoming more and more in vogue. We'll get into that. But Penzias Wilson came to the conclusion that they built a very precise detector that measured a background coming in all directions from every part of the universe and the sky that they could observe. That was unavoidable and inextricable, and you could not get rid of it. And so that became known as the 3 Kelvin. Now it's more precisely known to 4 or 5 decimal places, 2.725 Kelvin radiation background. That's now in the form of not light or ultraviolet or X-rays or gamma, but it's in the form of microwaves. About 2 millimeters is the most common wavelength of photons in the entire universe. And so my interest in that began in graduate school. I love to tinker with things. I always had telescopes since I was a little kid. I love working on cars, and I felt like, well, this is pretty cool. We could measure perhaps what had just happened, the fraction of the universe's history. And this was in 1993, the first evidence that the microwaves were coming slightly more intensely in different locations on the sky. The first deviations in perfect isotropy, which would preclude our existence in having this conversation if it were truly isotropic and perfectly homogeneous. But no, they had discovered, the COBE satellite in 1992 discovered that there were tiny fluctuations, about 1 part in 100,000, that were the reason effectively that we exist. The fluctuations in the fabric of space and time. And that was the year before graduate school.
I remember in the early 90s, people being a little bit panicked. What if COBE discovers that it is perfectly smooth? Right. What are we going to do?
Right.
And then astronomers saying, that's not going to happen. That's not going to happen. But there was this anticipation. What's going to happen? That fluctuation's going to be at the level we predict.
Right.
And just this huge sigh of relief when COBE said, okay, we don't have to panic.
That's right. Yeah. So for decades, 30 years almost since the discovery, then it was featureless. You couldn't see anything that was cosmological to indicate that we have reason not only to believe but to exist. And that discovery really transformed cosmology from a kind of qualitative science. They used to joke, Lev Landau, famous Soviet Nobel Prize-winning physicist, used to say, cosmologists are often in error, but never in doubt. And the reason that he would say that is because we were looking for things like the expansion rate of the universe, and very credible teams were getting a difference in the age of the universe ranging from 2 billion years to 20 billion years. And how could you have a factor of 10 error and call yourself a science, right? If you go and you want to measure the chemical atomic mass of a chemical, and you get it could be 1 kilogram or it could be 10 kilograms. I mean, who's going to have anything to do with it?
Well, I remember hearing lectures in the late 1960s where a cosmologist would say, "What's a factor of 3 among friends?"
That's right.
And he was excited. We got from a factor of 10 down to a factor of 3. Yeah. We're making progress. So
yeah, and now we're measuring these parameters, including the age of the universe, although teams disagree, which I'm sure we'll get into. But the level of precision is sub 1%.
Yeah.
It's become incredible. As I said, the temperature of the universe, the age of the universe, the composition, the mass, the energy budget, the amount of an obscure particle called the neutrino, and its fraction that contributes to the formation of structures in the universe. We know these things to sub 1% precision. It's actually a very precise science for the very first time. And actually, I always joke, if you go to the repository of all human wisdom and knowledge, you know what that is, Hugh? The repository of everything that humans have ever accomplished. It's called Wikipedia.
Wikipedia, okay.
And you look up not cosmology, you look up science. Science. What is the exemplar of all science? It's the history of the cosmos. In other words, the story of cosmology, tracing back, and even though it has an incorrect or possibly controversial statement at the very beginning called inflation, everything after that is backed by solid science, and we are working, my colleagues and I, to nail that first epoch called inflation down with our telescopes, including, as you mentioned, the Simon Observatory and the BICEP telescopes.
Right. And then, you were kind of going through all of this, and at the beginning of your career, cosmology had just started becoming a precision science. But I think what you can document is that the precision has gotten progressively better and better and better over the past, 40 years. And you actually had a hand in building the instruments to get that greater precision.
Yeah.
And that's a quest that you're still involved in.
Yeah.
So can you kind of walk us through, I'm glad you gave us your personal interest in this, but start with BICEP, go to BICEP2, and then these new instruments that you're working on, and basically explain how you've been able to increase the precision and what that has meant for establishing what kind of Big Bang universe we're looking at.
Yeah. So once the COBE satellite released the evidence from the temperature fluctuations that deviated from perfect isotropy, the hunt was on to really explain why those exist in the first place. We believe that they exist without them. They're kind of requirement for our existence. But nevertheless, we'd like to understand from a more primitive model why they behave that way and where they may have originated from. And then, of course, as I always say, flaws lead to new laws, meaning that it's not the compatibility with a pre-existing conception of a model that is really interesting to a science. That's interesting in a certain way. It's kind of like they've called it stamp collecting, and you collect more and more digits of precision. That's interesting, and it's important to do. And measure the lifetime of the muon to 10 decimal places or something like that. It's important, but it's not as fundamental, say, as measuring that the muon has a lifetime, that it may only be. So I'm interested in those big picture questions. So where did those fluctuations come from? There are many candidates for where they could come from, but there's one that's kind of become the predominant one, the one that has maybe become the paradigm for scientific research in the field of cosmology. It's called inflation. So inflation posits that the universe began expanding, which sounds trivial, but it's actually not, because there are many different modalities in which the universe could have begun from a black hole or an inverse of a black hole, or collapsed immediately, or come from a cycle, or been eternal. So there's many different alternatives to a singular Big Bang, a Big Bang with a singularity at its beginning. And so inflation posits that all of space and time is suffused with a quantum field, like this coffee cup is filled with coffee. But just like the coffee cup, there are tiny fluctuations in the creamer and sugar, and they're not perfectly isotropic and homogeneous throughout this coffee cup. That would take godlike powers of a barista quality that I don't even think you guys have here at RTB. But the fluctuations are what make this interesting, right? It's the departures from perfect symmetry that allow everything from life to exist to the formation of structures in the universe, et cetera. It's that the universe isn't perfectly symmetric. Inflation posits that the universe had tiny fluctuations in the amount of this field called the inflaton, which is for technically minded people, it's a quantum field, which means it is fundamentally not classical. It can't be described. You need to incorporate the laws of quantum mechanics, Schrodinger and others, Heisenberg in particular. And the value that it takes on, the energy that it takes on at a given point, which is all that matters to cosmologists, is how much energy there is in a given region of space-time. That is not constant. That fluctuates from region to region, and those fluctuations are tiny. That they're not zero. They're extremely small. They're not zero, and they vary from place to place. Those fluctuations in energy, according to a man known as Albert Einstein, are equivalent to mass fluctuations via the most important equation, E equals mc squared. So that means then, according to Einstein's second, I think much more important contribution to science, which is general relativity, the presence of mass changes the amount of curvature in the universe. And that curvature then changes the amount of gravitation that's felt by other particles that may exist, dark matter and ordinary matter. That then gave reason for the fluctuations to exist. So you had tiny fluctuations in a quantum field mandated by quantum mechanics that led to excess energy, which leads to effective excess gravity, or curvature to be technical, and that led to the agglomeration of matter, which then changed the temperature of photons, which then led to the pattern that we see. That's all well and good, but we don't have proof of that. We don't have proof that inflation actually took place. There's actually many different models that can replicate the pattern of fluctuations that Kobe saw, but what they lack would be what the inflationary model supposes exist, which are called waves of gravity, gravitational radiation that would have been present in the extremely early universe as quantum fluctuations of this inflaton field. Now, that's a big description that I've gone through. And not yet have I mentioned a single experiment. So the fact that these fluctuations exist then led scientists in the 80s and 90s, in particular a scientist by the name of Alex Polnareff, who became a mentor of mine working in the Soviet Union, to ask the question, what would a wave of gravity do to the cosmic microwave background photons? Now, you and I are old enough to remember photographic film, which, to any youngsters out there, used to have this sheet of, a polymer sheet, which would have silver and other particles on it. You have to expose it. It would get exposed to light in a camera, and then you develop it with different
Had to go into a dark room.
They had to go into a dark room so you didn't expose everything. What we're trying to do is expose waves, not of light, waves of gravity on a film. But that film isn't a material film. It's a shell of photons that we call the cosmic microwave background radiation. So when the CMB was formed 380,000 years after the Big Bang, that became then a shell of light that propagated to us. Right when it was being formed, if there are waves of gravity, it will cause a pattern in what's called the polarization of that light to persist that we can detect. To detect that light, we need a polarimeter, which is a telescope plus a filter. A telescope plus a filter. And the filter only lets in one polarization state of light, which is either vertical or horizontal. And then by mapping the polarization pattern on the sky, analogous to the way that Kobe mapped the temperature pattern on the sky, we can inextricably reveal the presence of these waves of gravity, which would tell us that this inflation took place, which then tells us potentially the existence of the multiverse, which is further downstream in our conversation perhaps. And so to detect it, you need a polarimeter. That means it has to detect microwaves of various frequencies in different polarization states. So in 2000
at very high sensitivity.
Extremely high sensitivity. You can't use your eyes to detect this light.
It's one thing to detect the temperature differences, the polarization of those temperature differences. You need an instrument that's nearly 100 times more sensitive.
Exactly.
And that's where you came in and say, hey, we need to have different telescopes that have the necessary sensitivity that we can get these polarization signals.
But the thing that I realized, thanks to a friend of mine named Mark Kaminkowski, who's at Johns Hopkins now, he used to be at Caltech when I was there, he had come up with an idea that you actually didn't need like a giant, he didn't phrase it in these terms, but I realized it was a consequence of his work, that you actually didn't need a giant telescope to measure these things. And then astronomers, as you know, we always want a bigger and bigger telescope. We went from, a 100-inch telescope not far from here on Mount Wilson to a 200-inch telescope down in San Diego, where I live, to a Keck telescope, which is even bigger than that. And then we had a Hubble Space Telescope, which is about 100 inches. Then we launched the 5-meter telescope, 6-meter telescope, the Webb telescope. And so we always want to get bigger and bigger. It's called aperture fever. It's a very healthy, but it's an addiction nonetheless.
Well, both of us had the experience of building telescopes when we were young.
That's right.
I loved your story about how, you were in a poor family and trying to get the money for it. For me, it was going around the neighborhood collecting beer bottles from drunks and cashing them in for 1.5 cents. Eventually I got enough money to buy a mirror and then built a telescope from it.
Fabulous.
So it's like, and then you say, hey, this aperture isn't big enough. I need a bigger aperture.
Bigger one. Yeah.
But you never lose that aperture fever.
But in the case of the cosmic microwave background's polarization, it turns out you don't need a big telescope, which is important because the cost of a telescope scales as the diameter to the third power. It's sort of like the volume of the telescope. So if you want a telescope that's twice as big, well, you better have eight times
as much money, yeah.
And that becomes prohibitively expensive. Whereas you can build a compact telescope, which has a lot of virtues. It can be shielded from the Earth's very high temperature. Room temperature is billion times more intense than the signals that we're looking for in the microwave background. So you can protect it. You can also make it very clean without any mirrors. Actually, the best telescope has no mirrors. It's just, you think about your telescope, the final product goes through lenses called your eye, which is a type of telescope, which has a lens in it, and then it's detected on your retina. Instead of detecting on your retina, we built detectors that are cold. Now, why do you have to build something that's cold? And why do you have to go to the South Pole, Antarctica? Well, we're looking for heat. Effectively, the CMB is a type of heat. And so just as you wouldn't build a good telescope nowadays in the middle of LA here, you'd be overwhelmed by its background, which would be light pollution. We want to go and get away from heat pollution.
Right.
So we not only have to go to a place that's very cold, we also have to get away from cool the detectors down to where a very low temperature state where they won't be contaminated by the telescope itself or the environment that they're in. And we also want to go somewhere very high up. Or ideally, we'd go to space. But going to space, I told you that the cube of the telescope determines the diameter, determines the cost. Well, to go to space, it doesn't matter. It's always going to be 1,000 times more expensive than building the same size diameter telescope on Earth. James Webb, about $12 billion. If it was built on Earth, it would be only a bargain at about $1 billion, or maybe even less. So,
and the instruments you were involved in, they're in the millions. We're not talking billions.
Yeah,
we're only talking millions.
Now we're at $1 billion. Now we're not quite yet at $1 billion, but the Simon Observatory at the end of it will be about $200 million.
$200 million.
So it's getting up there, but it's not in space. The reason for that is we have 300 people. It's mainly the people, not the technology, and we want to run for 15 years, and we'll get into why that is. So we realized we could build a small telescope, equate small with cheap, not free, but cheap. And I convinced, along with my late, great postdoctoral advisor, Andrew Lang, and Jamie Bach, who's a professor at Caltech now, we went to David Baltimore, a famous Nobel laureate, who was the president of Caltech. We said, we have this crazy idea for a refracting telescope. He's like, what, like Galileo did? Yeah, exactly what Galileo used. We're going to put it at the South Pole because the South Pole is the coldest, driest, highest continent. The Antarctic is the highest continent on average elevation. And it's important to be cold and high because water molecules absorb microwaves. So you don't want this light that's been propagating since literally the dawn of time to travel across the entire universe and then get absorbed in a water molecule, just like this coffee water molecules in here absorb the microwave energy from the microwave. So too would our atmosphere, if it has water in it, absorb it. So we decided we'd take it to the South Pole. We got permission. We built it there. It observed for 3 years, and then we upgraded it, just like Apple upgrades their phone every year. We upgraded it every 3 years. We went from 50 detectors to 250 detectors. Now the future incarnation of it, a current incarnation, is called BICEP4, or BICEP array rather, and that has 4 telescopes, and now we're up to like maybe 10,000 detectors. And the Simons Observatory will eventually have 100,000 detectors in it. So the rate of progress in producing these things and their sensitivity are increasing like Moore's law, and there's no reason why they can't continue to do so, except we will eventually reach a threshold not limited by the Big Bang, but limited by the cosmic local neighborhood that we live in called the Milky Way galaxy. And so that brings up this issue of the fact that we look out at the cosmos inevitably, invariably, through a dirty window. And that dirty window is our galaxy. It's not just the atmosphere. The galaxy in some ways is worse because it's astrophysical, so it's caused by something in an astronomical universe, but it's not cosmological. It doesn't tell us anything about the Big Bang or waves of gravity or inflation or the multiverse. So it's a nuisance to us.
Well, people I know who did research on the cosmic microwave background always told me our biggest problem is subtracting out all the stuff that's messing up our signal, getting rid of the noise from a Milky Way galaxy.
That's right.
Even the Andromeda galaxy's got to be taken out. That can mess things up. Yeah. And that, to do that carefully and accurately is not an easy task.
It's not. It's a big challenge for us. So we've developed tools to do it, but the general rubric in which these things go by is called systematic errors.
Yes.
They're either errors in your system, they're errors in the location of where you placed it, which could be you had to place it inside of a galaxy. Okay, well now you didn't spring for the extra $1 trillion to get it out of the galaxy or even out of the solar system. So you're gonna have to deal with that. And one of the ways, perhaps the only way you can deal with it, quote unquote, is to build a whole other experiment. You build another experiment that measures the unwanted signal plus the wanted signal, and then you subtract from the wanted plus unwanted, the unwanted, only unwanted. So that means we built a dedicated instrument to just measure the galaxy.
Which is why you can't use a single instrument. If you want to nail down the systematics. And in one sense, that's a good thing about astronomy. We're not dealing with unknown systematics. We know what they are, and our goal is to measure them. So many of the other sciences, especially the life sciences, we don't even know what the systematics are. So this is what makes cosmology precision, if you're willing to go to the effort of actually building the multiple instruments that are necessary.
Yeah, and it is a challenge. Like I said, it's the tax you pay for being lazy and staying inside the Milky Way. Just as you would not do very high precision astronomy looking through a car window, but if you did, you would do another experiment, quote unquote, looking at the windshield, and you'd see the windshield's dirty, and you'd get one of those squeegee guys out and they'd wash it off for you, and then you're doing another experiment. You're observing it, removing it, and so forth. We can't suck up the dust in the galaxy. And again, spoiler alert, my book's called Losing the Nobel Prize.
Right.
So the problem with the BICEP2 instrument, not the BICEP1 or the BICEP array instrument, is that it only operated at 1 microwave frequency, which was wise because we didn't think we'd ever detect anything. I mean, the first thing as a scientist you should do is expect that you're going to be wrong. As your friend, probably Richard Feynman, that you knew at Caltech from your Caltech times, like great Nobel laureate, he said the first principle is you shouldn't fool yourself. Right. And the second principle is you're the easiest person to fool. You should always suspect yourself, not of malevolence or fraudulence or anything, but just that you're likely to believe data that comport with your hypothesis and exclude data that seem to invalidate it, called confirmation bias. So we were originally, while my advisor, Andrew Lang, was alive, we were convinced that we would measure nothing. We'd never see anything because it's so outlandish that we could actually detect this signal. And then if we, on the off chance, happen to detect it, then we'd follow up on it and then see we'd get a lot more money, not just from Caltech and the president of Caltech, but from the NSF and maybe the Department of Energy or whoever. And they would then allow us to investigate very thoroughly and see, was it a systematic error? Was it a galaxy? Or...
You're bringing up something important here. There's a funding issue that's at the core of all research like this. So picking one wavelength where you can get high sensitivity measurements, if you find something, you can go back to the funders and say, now we have a reason to go for other wavelengths.
That's right.
So,
and in fact, that's what we've done. But at that time in 2014, exactly 10 years ago, we skipped that part where we went back. And we were so concerned that we would get scooped. And just as my grand advisor had by Penzias and Wilson, David Wilkinson was scooped by them. Bob Dickey famously said, boys, we've been scooped, when he heard that Penzias and Wilson measured this signal that they couldn't understand, but Dickey understood what they had measured, was the CMB. So the signals that we had seen at 2 millimeter wavelength or 150 gigahertz was exactly the right thing to do at first, which was to measure the CMB where it's brightest, which is at that wavelength. And then when we saw a signal, we went into kind of a panic mode because we never expected to see it. But we also had competition from a satellite in space, which was literally 100 times more expensive, called Planck.
Right.
The Planck satellite was saying that they were hot on the tail, that they could see this measurement if it was really real, and that they were threatening to release their own data. They didn't tell us what they had seen or what they hadn't seen, but they weren't sharing data with us. So that made paranoid, people like me, who's naturally paranoid, say, oh, they must have discovered this. There's a reason why they're not sharing information with us. They're good scientists, so they should have shared information. No, they were, sitting on it because they didn't have a detection. But what they had and what we lacked was information at other wavelengths that could have proven us to be the fool, that could have proven our hypothesis that we had discovered inflation to be nothing more than what it turned out to be later, that we'd seen dust in the Milky Way galaxy. Interesting, but not cosmological. Instead, we went ahead with it. I wasn't a leader of that experiment after my postdoc advisor, Andrew Lang, took his own life and died by suicide, tragically, in 2010. I'd been, kind of removed from the leadership circles, and I'd voiced objections to it, to going public with the supposition that we detected inflation, but they were kind of overruled by the leadership at the time at Harvard and University of Minnesota and Caltech again, and this was kind of set us off on a path that we really couldn't turn away from, and so it marched with this, drumbeat precision until it was on the front page of the New York Times,
right? Press
conference at Harvard, viral video at Stanford University, where one of the founding fathers of inflation was located, Andre Linde, and it was too late to unring that bell. And then for the whole summer of 2014, we were nervous, but we were expecting to be confirmed. And then eventually we had to partner with our very same competitors on Planck to realize that, no, we did not discover inflation. We discovered micrometeoritic grains of dust in the cosmos that's local to us.
Well, I remember that was embarrassing for your team, but
yeah.
Also I kind of remember that and saying, this isn't all that bad. They've now identified the dust.
Right.
This allows us to actually look at that in more detail and finally make the discovery we've been looking at all along. It's like, I personally saw it as a positive, not a negative.
That. I remember, and I quote from you, I think, in my book, because I remember being just so bemused as someone who had created the experiment that two completely diametrically opposite individuals, one named Hugh Ross and one named Lawrence Krauss, could both state that this was the discovery of all time, if confirmed and whatnot, which it wasn't. It was disconfirmed, as a matter of fact, not just not confirmed. It was disproven. But that you asserted this was evidence for the existence of God in one of your articles, and he asserted it was absolutely the opposite. We don't need a God; we can just have the multiverse, and we get everything. And of course, people were screaming that we were going to win Nobel prizes, but a lot of us had our doubts. And I came up with the title of this book on the night before the release because I realized either we're right, and we did discover gravitational waves from inflation, although that was so outlandish, but still, that was a possibility. But because I had been taken out of the leadership role of the BICEP2 experiment, I wasn't at the press conference, I wasn't in the New York Times, so I knew I would not win a Nobel Prize. Or we were wrong and we had made a blunder or mistake or even measured exquisitely precisely dust in our galaxy, which is an astronomical but it's not like, we thought we saw neutrinos traveling faster than the speed of light because we didn't plug in our fiber optics the right way, that we wouldn't win, nobody would win a Nobel Prize. And in fact, my prophecy came out to be true. I didn't win one, and nobody has won one yet. But it set the stage, as you said, for the tallest pole in the tent that, if removed, could give us indication of an inflationary origin in the universe. And that's where the Simon Observatory comes in.
Right. And as I understand the Simon Observatory, its quest is not just simply to show that there's an inflation event. I mean, we wouldn't be here if there wasn't inflation. So for anthropic
some
reasons.
Some disagree with that.
Yeah.
Some will disagree with you.
Yeah.
But go on.
That the real goal is what kind of inflation happened. And so it's like simply showing that it's inflated, that's the beginning of the quest. Finding out what kind of inflation is the real goal. So,
yeah, The challenge with that statement is that there are as many models of inflation as there are cosmologists,
Yes.
maybe even more,
Yes.
because I think everyone has 2 or more. So there's literally 200, 300 different models, quote unquote, of inflation, which is a big problem, right? You'd like to have just like one model. There aren't 200 models of general relativity. There's one.
Right.
You don't have to, determine, the speed of light 200 different ways in Maxwell's equations. And that's where there's some commonality and kind of common criticism between the opponents of string theory and the opponents of inflation. And actually, there are a vast number of very eminent, including Nobel Prize winners, who disagree with the notion that you exposited that inflation took place. I mean, there are models that don't invoke inflation for very good reasons, because not the least of which, inflation comes concomitant with a multiverse. And a multiverse admits every possible type of outcome, even those that are incredibly improbable, will, kind of manifestly take place. And I will be seated over there, and you'll be over here. You'll have written this book. I will run a place called Reasons to Believe, somewhere in an infinite space time of infinite universes. And it's a challenge that we have as cosmologists and maybe as people of faith as well, to how do you reconcile that, and I'm sorry to put on my podcaster hat, but I talk to my wife, I interview her on my podcast, but it's called a dinner date. So I can't turn down the opportunity to
Is that how she calls it too?
She calls it something else, but it's not polite to discuss on this YouTube channel. So I can't resist asking you, Hugh. But the fact that inflation is inextricably intertwined with the multiverse, which then provides reason for the explanation of fine-tuning, which then obviates the need for a designer, according to his proponents. I'm not stating my position here. How do you, as presumably intelligent design advocate, how do you reconcile those two facts?
Well, we've done a lot of work here in the multiverse. In fact, I've been speaking on it literally since the late 1970s. And just pointing out to people that there are different multiverse models. We can have the different Big Bang models. And the models that I find that are consistent are those that fit with the theistic worldview. The atheistic ones I find to be problematic in the sense that, I remember Leonard Susskind making the point, those of us who think there is no God, we've got to stop using the multiverse. It explains everything. An argument that explains everything explains nothing. And I remember giving examples to audiences in the early 1980s saying, consider the concept of infinity. And, lay people struggle with this and don't realize infinity times infinity is infinity.
Right.
So if you're going to appeal to infinity, you literally can explain anything you want.
That's right.
And so I use an example where I say, well, let's just consider an infinite number of universes where we look at infinity times infinity. You get an infinite number of planets just like the Earth.
Right.
And you get an infinite variety of life forms on those planets. And so I make the analogy is that you can even have an infinite number of birch tree species, one of which peels rectangular white pieces of thin white bark that fall in soils with random chemicals in it, and duplicate all the paragraphs, figures, diagrams, tables in every scientific research paper ever published, which would lead you to the conclusion those millions of scientific research papers didn't come from the minds of people like you and me. The multiverse did it. Right. And so there are philosophical traps that you got to avoid. However, there's real scientific evidence, particularly the inflation model, that tells us, hey, there's more than one space-time realm. And so, I think it was Max Tegmark who made the point, we need to realize there's different levels of the multiverse. Level 1, we don't dispute scientifically. There's good evidence for that. It's the level 4 we call into question, which is where you get into this infinity of infinity of infinities.
Right.
And so
mathematical structures, and then they get reified through some process that Max is a friend of mine and also quoted in the book. That is, of course, true. The challenge for proponents of inflation is that all the evidence that we have in the CMB is the most dispositive of it, because it's the oldest light in the universe. And so, of course, we human beings interact mostly through vision. And so even if when we don't talk about it, seeing actual optical photons, we still talk about someone's vision or their insight and their perspective, right? So these are all things that bespeak of our fascination and our fixation on the sensory optics that we have, even so much that most of our brain is dedicated to somehow processing these trillions of bits of information we get through our eyes. But when you take that into account, you look at the CMB, there are models that can explain every feature of it that don't invoke inflation. Now, there's way more work on inflation than any other cosmological, kind of origin, cosmogenic hypothesis. But if I say to you 97% of climate scientists also agree that, man-made global warming is irreversible and unavoidable, and we have to, you might dispute that. Or if I say to you 97% of theoretical high-energy particle physicists believe in string theory, you might also dispute that because that also leads to a multiverse. So it can't be the preponderance of people that believe in it, right? So that means that the humble reasoning of a single individual, as Galileo said, can overthrow the kind of complex notions of a maddening of crowds. So again, if inflation occurred, it's not clear that there's any better way to access it than through the observation of gravitational waves in the imprint on the cosmic microwave background, which is why I study it. But we haven't observed that. So how do you say with confidence that inflation we have evidence for inflation?
I could put it this way. I mean, for us to even be here, the universe has to be a certain size, and it needs to be thermally connected. Something had to happen to make all that take place within 13.8 billion years. And the most straightforward and easy way to understand that is through inflation. There are more complex ways to get that result. But how science operates, we go after the simple problems first and see if that works.
Right.
And if it doesn't, then we look for something a little more complicated. So I do agree with you, there are alternatives to inflation, but what we ought to pursue as observational cosmologists is that which we can get the funding for, that which has the greatest probability of giving us some success. Mm-hmm. And hey, if things turn out, and by the way, science always is more complicated than what we begin with. But we have to start with what we think is simple and straightforward and go from there.
I agree. I guess philosophically, however, those that say, echoing Karl Popper, that science should be predicated on those things that can be proven correct or proven, so to speak, even with circumstantial evidence, but rather on things that could be potentially disproven.
Falsifiability.
Falsifiability is one of the theoretical virtues that we appraise and apprise the efficacy of a scientific claim. So it's actually not possible to falsify inflation. Inflation could have occurred, and all the things that you say could be true. Actually, it could be that the universe, according to a good friend of mine, Rajendra Gupta, University of Ottawa, he believes the universe is 26 billion years old. Other scientists believe the universe didn't have a Big Bang and didn't start off in an expanding state based on James Webb Space Telescope data that we should look at. But the controversy that surrounds inflation is that of all the models, it's sort of the only one that can't be disproven or falsified, whereas a no Big Bang model could be falsified. A model of the universe that is so-called conformally cycling of Sir Roger Penrose, Nobel laureate 2020. That universe can be falsified. An ekpyrotic universe, a universe from string theory and membrane theory, that could be falsified. Mm-hmm. And a bouncing, non-singular cosmological cycling universe, very different from Roger Penrose, that could be falsified.
Right.
So of all the models that are sort of in play, quasi-steady state, steady state, eternal, and these bouncing or cyclical models, of all those, inflation is the only one you can't falsify. So how do you react to that?
Well, I mean, again, you kind of look at how science advances. I mean, I'm older than you, can remember when Big Bang had some good competition. Steady state, hesitation, the cyclical universe. And people were basically saying, okay, this doesn't work. I mean, right in this book, how they went from steady state to quasi-steady state.
Yeah.
Quasi-steady state held on a little longer, but eventually it got disproven as well.
Right.
And so science can advance by pursuing those things that we know we can disprove. So it basically focuses our research into a narrower and narrower realm of investigation. And that's a worthwhile way to go. Yeah. But I think you'd already discussed this. one of the complicating factors in all this is the philosophical and theological implications that you discussed with Ken Samples. And so now our theology, our philosophy gets in the way of how we interpret all this data. But I think that's what makes it exciting for lay people and for the funders. They'll say, hey, the fact that this does have philosophical implications, this is worth pursuing.
Yeah.
But it also means we need to be very careful about our biases.
That's right. And there's a tendency, with all scientific endeavor, there's a stereotype that science is done by these dispassionate walking Wikipedias, and nothing could be further from the truth. We have biases. I mean, something like if you just took all scientific papers, I told you Wikipedia has, cosmology, the standard Big Bang model is its example of what science is. All right, it's prima, example. It's put up on the beginning of the page of all of science. But there's a stereotype that we just, we just go through life. But if you take all of scientific research and you ask, well, what fraction of scientific claims are replicable? Just replicable. It could be in medicine. It could be in biology. It could be in origin of life study, whatever. And it's like 5% or something. It doesn't mean they're fraudulent. It doesn't mean they're wrong. It just means there was a study, and sometimes scientists will do what's called p-hacking, and they'll find different contortions of the data unbeknownst to them that tend to provide a excess statistical significance that then can be published because there's a bias against publishing null results. In fact, that would have held true, to this very day. We have not detected these waves of gravity. We have not detected the strongest form of evidence that would indicate inflation took place. But again, not prove it, because you could always have a mechanism that exactly replicates these waves of gravity.
Well, something you addressed in this book is that in science, there's often an insignificant appreciation for the value of a null result.
Yes.
Null results are important. And it's worthwhile to dedicate your career to proving what doesn't work and what's not.
That's right. Yeah.
Now, I want to talk a little bit about this Simon's instrument, because it's an instrument that you're working with, and they just had first light. And to really get an understanding of what's happening during the inflation era, you need to have accurate measurements of not just one mode of polarization, but both.
That's right.
The B is especially difficult to get. So, but as I understand your project, you're basically targeting that. We're going to get accurate measurements of the B mode, but I also appreciate that you're telling the public, be patient with us. We're not going to be able to do this in 1 or 2 weeks.
Right.
So tell me, what is the objective of the Simon's instrument, and when can we expect results that might change our whole picture of what kind of Big Bang we're looking at?
Yeah, so the Simon's Observatory is really,
Tell us where it is, first of all.
So it's in the Atacama Desert of northern Chile. It's at an altitude of 17,200 feet above sea level, so you have to wear...
Question.
Yeah.
Have you ever been there?
I've been there 4 times.
4 times, and you survived.
Yes, exactly, yeah. You can go there. It's actually a tourist, the tourist destination. It's outside of a very quaint, charming Chilean town called San Pedro de Atacama. There's active volcanoes nearby. There's a 20,000-foot dormant volcano, they tell me. I haven't climbed to the top, but my graduate students that are in better shape than me have climbed up to the top. There's a beautiful lake. I mentioned climbing to it's the highest lake
20,000 feet?
20,000 feet, about 7,000 meters or 6,000.
So how long did it take you to adapt from sea level to going to 17,000?
We require that you spend one night at 9,000 feet or so. That's where San Pedro is. And then the next day you can go up. You're wearing oxygen and a cannula in your nose. You're wearing hard hats, UV protection. It's extremely bright, brilliant sun up there.
Oh, so you actually take oxygen with you.
Oh, yeah.
I thought you were going up there without oxygen.
No, there's oxygen either in bottles or there's concentrators that concentrate the atmosphere, because there's half the pressure that you and I feel here at sea level. So in fact, it would be illegal to fly in a plane at that altitude without pressurization or supplemental oxygen. So that's just a tidbit. It's actually illegal at 12,000 feet, let alone. And every 1,000 feet, since the atmospheric pressure is decaying exponentially, it's an incredibly different experience if you've ever been to the Sierra Nevadas, even though they're at 14,000, 13,000, or Colorado and Aspen.
Well, I've noticed a difference between being at a 13,000-foot peak and 14,000. It's only 1,000 feet, but you notice a difference.
Yep.
Yeah.
And even more so at that altitude. Thank goodness, I've not had any problems at that altitude. Some people get sick. There's medications that you can get prescribed before you go there to help with it. And there's all sorts of different diseases that you can get, high altitude pulmonary edemas and stuff that you have to worry about. And they can strike at any moment. But we have people as old as, I had Jim Simons come up there. Unfortunately, he passed away in May. But he was there when he was 79, and he smoked 3 packs of Merit cigarettes for 57 years. So he made it up there only for an hour, but we were up there. It was fine. It wasn't like he wanted to come down, but that was in 2019. And so the Simons Observatory is funded by the Simons Foundation, the Heising Simons Foundation, partner universities, including UCSD, Princeton, Penn, Berkeley, Chicago, and many other institutions. And it's a $110 million construction project that just finished, as you said, in April, right before Jim Simons passed away on his 86th birthday. We were able to share the first data points. I won't share them with you. They're confidential for now. They're embargoed for now, but we should have results soon. So there's 3 telescopes, similar in concept to BICEP, because that's how I think, and was involved in the original, proposing to Jim, who's been a lifelong friend.
And do you have a slide of the instrument?
I don't, but I'll send you the cover of the Science Times from the New York Times, and you guys can put that in. Drone shot of the observatory, some pictures of the telescopes that I took when I was there in March. And it's an exquisite environment, and it's very different from the South Pole, where I've been twice. The South Pole is the most boring, flat, desolate, ice planet-like world. There's nothing to do there. There's no, tourists there. It's just a couple of dozen people, military and scientists, and that's about it. Wonderful people, but it's not the kind of place that I'm happy to spend more than a day or two at. But
not a vacation destination.
No, the first time you go there is enough for your whole life. Some people love it, and there's a competition to spend a year of your life. Can you believe there are these people that want to spend a year of their life at the South Pole? And there's a hot competition. You have to pass psychological tests, physical tests. You have to have.
I remember you describing that in here.
Yeah. So all that. So it's different, but the reason we're going to these great heights, literally, is to get above water vapor in the Earth's atmosphere. So the Simons Observatory will have 3 telescopes, currently has 3 telescopes like BICEP, although much more sensitive, much more advanced, many more detectors, and operating crucially at, instead of 2 frequencies, we're going to operate at 1 frequency, instead of 1 frequency, 6 frequencies. So we can see the CMB, the cosmic background, plus we can see the dust in our galaxy, plus these electrons in our galaxy that make this type of contamination called synchrotron radiation. So we can measure not only the signal of interest, and in fact, we spend more, total number of detectors or data looking for the contamination than looking for the signal. And the detectors
that's important.
Extremely sensitive detectors. And these are made of superconductors. So a superconductor is an exotic form of matter that, as you cool it down, eventually it reaches a point where it has 0 resistance. The resistance drops, and then all of a sudden goes to 0. These were discovered in 1904, 1905, when helium was first liquefied. So you can transmit energy with no resistance. But between the point where it has a finite but small resistance and 0 resistance, there's a transition. It makes a transition where the resistance is extremely temperature dependent. And so what we do is we make this resistor operate right in the middle of that transition. And so it becomes one of the most exquisite thermometers you can get. So sensitive it can detect few thousands of photons hitting it from the early universe. They had to make their way through the entire cosmos, the galaxy, the atmosphere, then go through the optics of the telescope. Then they land on this tiny little detector. And it's a superconductor, so it'll change its temperature, and we measure its change in resistance very exquisitely. And we can have thousands of these things printed in an area a little bit less than this area of this table.
How much liquid helium do you need for this?
0. Oh, we need some, but we just call it a dilution refrigerator. So BICEP used actual liquid helium. So we would pour in. There was a person who'd spend his winter there, which is 9 months plus, and he would every day or every couple of days have to dump in liquid helium into it. We've gotten away from that in the field. It's very expensive. Helium is almost a precious commodity now. It's a rare commodity. It's becoming harder and harder to get. And instead, now we have what's called a dilution refrigerator, which mixes different isotopes of helium. And by doing that, it achieves a cooling temperature that's continuous. So you never have to dump in and then boil off helium into the atmosphere.
A lot cheaper then.
Yeah, it's a lot more upfront cost, but it's really logistically, it would be impossible to run these detectors.
Okay, now how long is this experiment going to need to run before we get a really accurate measurement of the B mode?
So currently, BICEP made this mistakenly identified cause of the B mode polarization that we saw.
Right.
We claimed it was inflationary gravitational waves. We claimed that therefore it was evidence of the we didn't write that, but we claimed it was the first direct evidence of inflation, effectively.
Right.
And then that was disproven because we measured, in fact, instead with the Planck team, we measured actually most of the signal, if not all of it, was caused by dust in the galaxy. So, but BICEP hasn't stopped. They didn't make an error. They didn't have to shut down in humiliation and embarrassment.
They just said we need more time.
We need more frequencies.
Yeah.
We need more systematic errors to be measured. We need more time. And so they've upgraded. So I invented BICEP1 with colleagues, and then they upgraded BICEP2, was the one that made the announcement prematurely and incorrectly of gravitational waves. And then but there's been a third generation, BICEP3, and the fourth generation is called BICEP Array, which is 4 identical refracting telescopes on a single platform exactly at the same location at the South Pole. They're going on, they're going to observe for more. And they've actually continued to reduce and set upper limits or null detections.
Right.
They have not detected the signal. They're continuing to improve. They are the world's best. They're better than the Planck billion-dollar experiment. They've done far better than what any of my other experiments like Polar Bear has been able to do or anything. And the Simon Observatory will only be able to catch them after 1 full year of observing, will be about the level that they've achieved over the last 14 years or so.
Right.
So that's powerful and that's great, but what we don't want to do is go beyond them.
Right.
And so to go beyond them is going to take another 3 years. So we're funded for 3 years. We're
4 years total.
A total of 4 years, and then after that, an observatory led by an upgrade led by Mark Devlin, who's a partner and collaborator friend of mine at UPenn, and Suzanne Staggs at Princeton, called the Advanced Simons Observatory. It's going to take over, and we'll get another 4 or 5 years of observing. And then potentially it will partner with the BICEP folks and other folks from the South Pole 2030 or something like that. So this could keep going for another decade before, and you never know where it could be. It could be inflation took place, but a very low energy scale, quantum fluctuations, which would lead to small B modes, which would take longer time to detect. So for now, it won't do anything except detect noise and make measurements of the E mode polarization. Eventually, if inflation took place, we should see B modes, or we should see it from other sources. But the cool thing about the Simons Observatory, unlike BICEP is only a refracting small tabletop diameter telescope. It's much bigger in reality, but effectively it's like a refracting telescope with this diameter that's about 2 meters long, and a platform that it sits on. But the Simons Observatory has another telescope called the Large Aperture Telescope, which is 6 meters. 20 feet in diameter, which can measure a host, 40 different types of cosmological and astrophysical signatures, ranging from the mass of neutrinos to the evolution of dark energy, the amount of dark matter, and even detect Planet 9 with a CMB telescope, but only possible because of its large apertures. Totally different capabilities than BICEP.
And you're going to be able to get a better measurement of the ratio of hydrogen to helium too. So
we don't directly measure that parameter in terms of the hydrogen ratio. That's more the cutting edge there is in stars, either old stars or called population 2 stars, or even local stars that are metal poor and have different. So the amount of helium is not as considered as big as an open question. There's something called the lithium problem, where lithium is one of the primordial elements that's not well constrained in the standard Big Bang model. It seems discrepant at a few standard deviations. That will also be measured by optical astronomers. So it'll be a little bit different scientifically.
What I'm excited about, though, is that if you integrate what you get from, say, James Webb, which is now actually finding clouds in the halos of galaxy, where it's just hydrogen and helium. And you've got the Lucy instrument, which is going to be in the backside of the moon. Combined with the cosmic microwave background, we might be able to get a better number on that. And that'll get us. I think
I have a slide, if you want to show it, of this one here. Yeah, so when you have a source of light, like a star, a galaxy, even a quasar, quasi-stellar object, that they provide a backlight, and they can then be used, if you understand their properties, to determine everything that's happened to light along the way from source to observer. And so astronomers, including my friend David Zeitler at UC San Diego, and others have been using this technique for a long time to measure these absorption features, which would then be indicative of the primordial abundance, the original abundance of things like hydrogen and its isotopes. So this is an exciting field, and also the ignition of the first stars, the so-called the end of the cosmic dark ages. That's an open question that astronomers, I think we'll even have it before this Lucy experiment on the moon because there are experiments in Canada and elsewhere in South Africa that are looking at this epoch of, it's called reionization, which is
Right.
ignition of these new stars, the first major event after the CMB.
Yeah. So there's real excitement going on
Yeah.
and being able to integrate all these different epochs.
Absolutely.
I mean, when I was young, the idea that you could explore the first 2 billion years of the universe was considered a pipe dream.
Yeah.
And we said, okay, a cosmic microwave background, that gets us the first few 100,000 years, but then there's this vacant window.
That's right.
And this vacant window now for the first time is being filled in.
That's right.
So-
yeah, those flaws need to new laws.
And now you guys are being able to give us an accurate number on the B mode polarization.
That's right.
So a lot of exciting things that we can look forward to.
Absolutely.
And I'm glad to hear that we're probably going to have good numbers within a decade.
Yep.
And maybe even something that you can release ahead of time. I expect that you'll say, hey,
I'll call you up. Yeah.
after 2 or 3 years, this is where we are so far.
Yes.
This is the direction it looks like it's going, and basically give people more anticipation.
That's right. Yeah.
Of course, the funders love that too.
The teasers. That's right. Yeah. So we should have, exactly. We should have.
So when can we expect the first tease?
Well, we're already preparing my students and all others on the Simon Observatory right now in Japan at an international gathering of nerds called the SPIE, Society of Photometric and Industrial or Imaging Engineers. And we present our first data from the telescopes, which we started acquiring back in October 2023, and that those data, the initial data, were actually, it tickled me because we looked at, what did we look at? Well, we're using a refracting telescope. First thing you do is look at the brightest things in the nighttime sky. Well, what's that? Jupiter and the moon. Well, guess who else looked at Jupiter and the moon and Saturn?
Right,
It's
right.
Galileo, who invented the modern version of the refractor. He didn't invent the refractor, but he perfected it. He improved it. He removed systematic errors in the optics and the glass, and understood the mathematics of it to then use it to test a high scientific hypothesis. What was it? That the Earth was not the center of the universe, and of course that led to the real culmination led to the scientific revolution that took place after his untimely imprisonment and death in 1642.
Well, you know what? Maybe I can convince you that when you do have something to tease us with, we'd love to have you come back.
Yeah, absolutely.
And give us a little update what's happening. And but what excites me over the past 60 years is just how astronomy has taken this discipline of cosmology from being incredibly vague, mysterious, where we're happy with a factor of 3 amongst the different models.
That's right.
Now we're getting down to a few percent.
Some percent.
But it's like we're making progress
Yeah.
and being able to understand what kind of universe we're living in, how it's all put together, why we're able to be here at this time. And so I'm really thrilled. And because I was thinking, are we ever going to get an accurate measure of the B mode?
Right.
I thought maybe that's never going to happen. But
It still might not.
It still might not,
You always
yeah.
have to be open to that possibility that nature is under no obligation to make the universe measurement and its properties accessible to human beings, at least not now. I mean, imagine if you lived in 1865, 100 years before Penzias and Wilson. You would have thought, like Einstein did, universe is static, eternal, never unchanging, even up until 1928. He believed that. So for those reasons, it's an incredible time. But again, there's not necessarily a guarantee that we'll see them.
there's a possibility
There's a
that
possibility.
the B mode is so weak that
Yes.
even with the great Simon instrument array,
That's right.
you're not going to be able to find it. But it's kind of like deja vu. We were there back in the 1960s and 70s and basically said, well, with just a little bit more funding, we might be able to get down to a level. And so even if it does prove, even if all you get is an upper limit,
Yeah.
that to
And
me would
actually,
be an exciting
we're guaranteed
advance.
to not only get an upper limit. We're
Yeah.
guaranteed to measure things like particle physicists have dreamed about for years. The neutrinos are elementary particles. You cannot carve them into other particles. They're fundamental, indivisible particles, we think. And neutrinos have a mass that is unknown what its exact value is. We have a lower limit. It can't be smaller than a certain value. It also can't be bigger than a certain
Right,
value.
right.
But that's like me saying you weigh more than 0, but you weigh less than 1,000 kilograms. Okay,
Right.
thanks. It's interesting. You didn't prove infinity or whatever. You made a prediction, unlike, say, string theory. But in this case, no. It's very, very precise. But we will measure those with the Simons Observatory. we get science because of this large aperture telescope.
And
Simon's
you're going to be able
observatory.
to tell us it's just 3 and not 4?
We could say if there's more than 4, more than 3. We could say if what their mass actually is, which is traditionally, if you think about that, that's revolutionary.
It is, yeah.
We've never measured the mass of a particle in space, like from a cosmic observatory. We've only done it from laboratory experiments. Never once did it from measured a quark, floating from Proxima Centauri.
Okay. How precise of a mass do you think you can achieve of the 3 different kinds of neutrinos?
Yeah, so neutrinos are what are called weakly interacting massive particles. What we know is that there's at least 3 of them. There could be more. They could have other properties, but let's just say in the what's called the standard or normal hierarchy of neutrinos.
We know there are 3.
Yeah, we know there's at least 3. We don't know their mass, the hierarchy, in which is the electron neutrino heavier than the muon neutrino or this one. We only know right now we have an upper limit and a lower limit on the sum of their masses.
Right.
We will, with the Simon's Observatory in combination with other instruments like Vera Rubin instrument and the DESI instrument, we will then not only determine if the hierarchy is normal or so-called inverted, but we can get down to a precision which is smaller than or better than the minimum mass difference between these neutrinos. In other words, we'll be able to detect what order that they're in. And once you know the order, you know that, say, 2 of them will be massive and 1 could be massless or it could be very low mass. And we can measure that lowest mass state, and therefore we can get a set of what is the hierarchy of the neutrinos and constrain their total sum. And so knowing the sum and the individual hierarchy, then you basically know what their masses are.
Well, Brian, even if we get nothing on the inflation, if we get that in the neutrinos, it's huge. That could win you a Nobel Prize.
Sure. But I tried to disabuse myself of pursuing that idol worship in my first book. But no, you're right. And in fact, it's even better than that, because there's even controversy now. If you take the cosmic energy pie, say every photon, every proton, every neutron, every crouton, you put everything into a pie.
Croutons, I haven't heard of those.
Yeah, those are my favorite, most delicious particles. Reminds me of lunch we're supposed to get soon. And you took it and you wrote the cosmic energy budget as a pie chart. You'd have about 70% would be dark energy, 24%, 25% would be dark matter, and then 5% would be everything else, including like just plasma of hydrogen gas and stuff like that. And then in the 1% or less would be elements like calcium in our bones and potassium in our DNA and all these incredible molecules. It almost makes up nothing in the cosmic energy budget. But that huge second chunk, dark matter, we don't know what it is, but we know at least we've detected one version of it, and those are the neutrinos. So they're an existence proof. They prove, shadow of a doubt, that at least there are some particle versions of dark matter. There are people that believe dark matter itself doesn't exist by virtue of what's called modified Newtonian gravity, and they think we don't understand how gravity works, and you have to change gravity.
Well, I just saw a paper last week making the point that maybe primordial black holes make up a significant fraction of the dark matter.
Mm-hmm. It would still need to explain why they have the properties in galaxy halos that they do. We believe that the galaxy halo extends 10 times the visible starlight radius.
Oh, yeah.
So they'd have to be out there, and we don't see their gravitational effects on more distant light. So that's a controversial hypothesis, but it's interesting to propose.
And why the Milky Way has such a big one.
Exactly, yeah.
Now, there's a lot of exciting things we're talking about here.
It's
so
the
it's
most exciting time to be in cosmology, which is why I'm glad a 30-year-old younger version of me chose this field to begin with.
All right. Well, this has been great. Love to have you back and talk about it when you got some initial results.
Absolutely.
But thank you for joining us today in Stars, Cells, and God. Join the discussion in the comments below, and remember to like this video and to subscribe for more content. Subscribe to our YouTube channel. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend. Remember, the more we know about science, the more reasons we have to believe in Jesus Christ as greater Lord and Savior. Thank you.